Hello, Advanced Algebra 2. Welcome to the Concept 32 notes. In this set of notes, we're going to look at recursive rules with sequences. So far, we have been writing rules for our sequences using explicit rules. A recursive rule refers to the term in front of the term. Sometimes it refers to two terms in front in the list. All right, so let's get started. Let's start by looking at some sequences, and let's determine if they're arithmetic, meaning a linear pattern, geometric, something like an exponential pattern, or neither. We're going to write an explicit rule for these sequences, if we can, in terms of the nth term. Okay, so we've got our first sequence, 3, 6, 9, 12. So that our difference is we're adding 3 every time. So if we are increasing by a constant, then that'll be an arithmetic sequence. So let's use that formula that we learned to write the rule. So any term a sub n will equal our first term, which is 3, plus our difference, which is also 3, times n minus 1. Now let's look at b. We have 18, 14, 10, 6. Right away you can tell that we're just decreasing by 4, by a constant value. So that's a common difference of d, and that's an arithmetic sequence. So we can write our rule using the same formula. Any term a sub n equals the first term, which is 18, plus our difference, but since we're subtracting, that'd be minus 4 times n minus 1. Now let's look at c, 3, 6, 12. So the relationship is that each time we're multiplying by 2. So now we have a rate, a common multiplier, so we have a geometric sequence. So let's use that formula that we learned in how to write a rule for a geometric sequence. So any term a sub n equals our first term, which is 3, times our multiplier, which is 2, raised to the n minus 1. Okay, now let's look at d. So 128 down to 64 down to 32. Notice that we are decreasing by half each time. Think of it as a multiplier, multiplying by half. So that gives us a geometric sequence. So using our formula, any term a sub n equals our first term, which is 128, times our multiplier of a half raised to the n minus 1. Now, e is interesting. It's just 5, 5, 5, 5. You can think of it as multiplying by 1, but that doesn't qualify as a geometric sequence. We need to be multiplying by an amount other than 1. So this would be neither for our description. We can write a rule. It's just any term will equal 5. All right, and then finally, we have a sequence that you may be familiar with. 1, 1, 2, 3, 5, 8. So if we look at it, especially from one term to the next, notice how the term that we get, we have to add the 2 before it. So to get our third term, 2, we add 1 and 1. To get 3, we add 2 and 1. So that doesn't qualify as either, and we're not able to write a explicit rule for this sequence. This is known as Fibonacci's sequence. Later we will write a recursive rule for it. All right, so far we've worked with the explicit rules, like I mentioned, for the nth term of a sequence, such as a sub n equals 3 times n minus 2, or that's an arithmetic, a sub n equals 7 times 1/2 raised to the n. That is a geometric. An explicit rule gives a sub n as a function of the term's position number, n. Now we're going to learn another way to define a sequence. This is by a recursive rule. So a recursive rule gives the beginning terms of a sequence and a recursive equation to tell how any term a sub n is related to the one that comes before it. The notation that we're going to use to show the term that comes before a sub n is just a sub n minus 1. That just means the term before. So if you look in the box how to write a recursive rule for an arithmetic sequence, we have any term a sub n equals the term that came before plus the difference. Now we are going to need to give a starting term with this rule. Otherwise, you won't be able to generate the sequence. Look at how to write a recursive rule for a geometric sequence. So any term, a sub n, will equal our multiplier times the term before. Again, look at the note. This is very important. With a recursive rule, it's part of the rule to give at least one starting value. So let's look back at our sequences in our exploration, and let's write recursive rules for those. So our first sequence was increasing by 3. It was arithmetic. And so if we think about it, we wrote a explicit rule. A recursive rule means that we're going to take the term that came before and add 3. And then we need to give a starting term. So if someone's trying to generate this list, this sequence, and doesn't have it in front of them, they can take the first term and just go from there. All right, our second sequence was also arithmetic, 18, 14, 10. We were decreasing by 4. So what we can do is write a rule where we take the term that came before and subtract 4. And then we'll give our where to start the sequence. So our first term is 18. Now remember C, that sequence was geometric, so multiplying by 2. So any term will be our multiplier, 2, times the term that came before. And then we need to give a starting number in case someone needs to generate the sequence without seeing it in front of them. All right, now D was also a geometric sequence, so starting with 128 and decreasing by a half each time. So we're writing a geometric recursive rule. So that would be our multiplier, which is a half, times the term that came before. So we write that as a sub n minus 1. Our first term is 1. So we're going to skip E, and let's go to F, the Fibonacci sequence. Now, the trick with the Fibonacci sequence is that to generate a term, and we start with the third term, you have to add the 2 terms in front of it. So to show 2 terms in front, we're just going to have a sub n minus 2. Plus a sub n minus 1. And then we need to give 2 starting terms, there we go, for our Fibonacci sequence. So we can write it using our recursive rule with 2 starting terms. Now let's look at this example here. We're going to evaluate recursive rules, writing the first 6 terms of each sequence. So notice now our first term is actually a sub 0, and that equals 1. And then we have the arithmetic rule that we take the term in front and we add 4. So let's start with our first term, a sub 0, which is 1. And then to get a sub 1, we simply add 4, which will give us 5. To get a sub 2, we take 5 and add 4, the term before. To get a sub 3, we take the term before, which is 9, and add 4. So recursive rules, you need to have the term that came before in order to generate the list. Now let's look at B. This is function notation. So our first term is 1. And then if you look at the rule, you can tell that it's a geometric sequence because we're multiplying by 3. So to get our second term, we'll take our term that came before times 3, 3 times 1. To get our third term, we'll take 3 times the term that came before, which is 3, so 9. To get the fourth term, we'll take 3 times the term that came before, which is 9, to get 27. And hopefully you see the pattern. So 27 now times 3, 81. So each time we're multiplying the term that came before by 3. Now let's look at A. So A, we've got our Fibonacci sequence again. So we know that we're going to take the term that came before plus the term that came immediately before, and then give ourselves 2 starting numbers. Now for B, this is kind of a tricky one, so look at this one with me. All right, so our first term is 1. Well, in our list that we can see, 1, 1, 2, 6, 4. So you think about, how do I generate that? Well, if I take the second 1 in the sequence, and then I multiply it by the term that came before, then I will get that term. So 1 times 1 is 1. So now figuring the third term in the sequence, if I take the term that came before, which is 1, times my n value, which is 2, I will get that. So we're going to start our numbering at a sub 0. That's how that will work. So we take our position number times the term that came before and start ourselves at 1. Now let's translate between recursive and explicit rules. So let's write a recursive rule for A. And notice A is an explicit rule and it's a geometric sequence. So A sub n equals -6 plus 8n. So my first term, I can see if I plug in 1, I get -6 plus 8, which is 2. And if I plug in 2, -6 plus 16 is 10. So I can see my difference is 8. So now to write a recursive rule, I will say that any term, a sub n, equals that difference, 8, plus the term that came before. Or I could write, a sub n minus 1 plus 8. And then I give my starting first term, which is 2. Now B, we are given an explicit rule, again, so we need to translate that to recursive. And notice that this is geometric, all right? So let's go ahead and pick out what our first term is. Plugging in a sub 1, that will be -3. And then notice what our multiplier is, which is 1/2. So for our recursive rule, we take our multiplier, which is 1/2, times the term that came before, and we give that along with our first term. All right, now C, I've got an explicit rule for this arithmetic sequence, and I want to write a recursive rule. So I'm going to look at the first two terms. So I plug in 1 and get 13, 2 and get 9. So I can see that my difference is 4. I'm subtracting by 4. So for my recursive rule, I take the term that came before and I subtract 4, and then I give my first term that I'm starting at, which is 13. All right, and then the last one with these, we have an explicit rule for a geometric sequence. So I have my first term. If I plug in 1, I get 16. I see that my multiplier is 3, so my recursive rule is that multiplier 3 times the term that came before, and then I give my first term as 16. Now let's translate between, go from recursive to explicit rules. So I've got an arithmetic sequence because I can see that I'm decreasing by 2 and I know my first term. I'm going to go ahead and just list out some of these. All right, so my explicit rule will be my first term plus my difference, and in this case it's -2 times n minus 1. Now let's look at B. So we've got the recursive rule, a sub 1, which is 10, and then 2 times the term before. So our multiplier is 2. So as an explicit rule, we have a sub n equals our first term, 10, times the multiplier, 2 raised to the n minus 1. Now let's take a look at C. So let's write out a few terms of this sequence. -12, we add 16, we get 4, 20. Our difference is we're adding 16 each time. So any term will equal our first term plus our difference times n minus 1. And then finally we're back to a geometric sequence example. Our multiplier, our value, is -6, and we're going to change this recursive to an explicit. So a sub n equals our first term 2 times our multiplier -6 raised to the n minus 1. Let's look at this real life problem. So a lake initially contains 5,200 fish. Each year the population declines by about 30% due to fishing and other causes, but the lake is restocked with 400 fish. Write a recursive rule for the number a sub n of fish at the start of the nth year. So a sub n will equal that beginning amount, the first year will be beginning amount, and then each year the population declines by 30%, so what's left is 70%. So that will be our multiplier. So 0.7 times the term before, the year before, plus the 400. And then our first term will be 5,200. So we need to find the number of fish at the start of the 5th year. So at the start of the first year, A sub 1, we have 5,200. At the start of the second, we have 70% of that plus 400, which is 4,040 fish. At the start of the third year, we have 70% of that number plus 400 equals 3,228 fish. At the start of the 4th year, we've got that amount and 70% of that plus the 400, which will give us 2,660. And at the start of the 5th year, we have 70% of that plus those 400 fish. Now, on your calculator, keep doing that same pattern and see what happens. As you'll notice, what happens is that the population of fish will level out. It will get close to around 1,300 fish, or about 1,333 fish. And the reason why it approaches that amount, because that's the amount that if you take 30% of that amount, it is about equal to the number of fish that are being restocked in the lake each year, 400. All right, that concludes our Concept 32 notes.